All right, this next lesson is referring to composite functions, And with composite functions, or sometimes people refer to as fog, all right, what we're doing is we are creating a function inside of another function. You use this a lot when you're dealing with inverses, okay? Inverse functions, exponentials, and logarithms, and when you get to calculus, you use it in the chain rule and various other topics. So composite functions are kind of a big deal. Yeah, really big deal. All right. Now, when you see composite functions, a lot of times it's written as f of g of x. Or if you want to compose the other way around, g composed of f of x, that would be g, and the function f would be inside of g of x. So you have a function inside another function. When you see this, you also see f with this little circle. Looks like a 0 or a multiplication symbol. It is not, because it's not filled in a circle, but it's what's known as a composition. Okay, composition. So you're plugging whatever's on the left inside the function, sorry, whatever's on the right into the function on the left. Now, whenever I think about functions, I like to use this analogy, is if you've ever seen Shrek, all right, you have functions which are known as ogres. Okay, functions are ogres. And they're ogres because ogres are like onions. And onions, as we know, have layers, because ogres have layers. You're still a donkey. Oh, no, Shrek, I like parfaits. And you can go with parfaits, and you can do the imitation of Donkey and Shrek and all that stuff. But that's my bad imitation of that. But functions have layers, because you are peeling away or trying to figure out what layers inside another function. So, for example, all right, as we peel back the layers of this function, if we say h of x, which is equivalent to f composed of g of x, f composed of g of x, all right, which is f, g of x is inside f of x, all right, and let's say this is the function, all right, so let's peel back the layers. If we see this, we can say, okay, what is the outside layer? Well, I always look at it and say, okay, if I have an outside layer, I kind of see parentheses or square roots or roots as the first layer. So if I peel off this, and I go, reach it over, if I imagine my hand right here, here's my hand, all right, reaching over and peeling back this layer, and then I'm crying, because here I am, and I'm crying, oh, because it's a onion, all right, that's a bad, I'm trying to make this tutorial somewhat funny. But as you peel back this layer, all right, what you realize is that the first layer you peel off actually is a square root function. And we'll put square root of x. All right, so the first layer is square root of x. The next layer, if we peel that out, what is left over? Well, the thing that's left over is stuff inside, which happens to be x squared plus 3. So we actually have a composite function. We have f of x composed of g of x. If I take this function, g of x, and I plug it inside the square root, I have the square root of x squared, all right, plus 3, which we have right here. So that is a composite function inside other functions. Okay, so let's do an example of this. One, if I were to find, given our two equations, and I want to find f composed of g of x, that means I'm taking function g, all right, and substituting it in and plugging it into function f. All right, so f, if you recall, all right, these are the input slots. Okay, so I need to take this and plug it into here and into there, because this is my input. So what we have is we should have x cubed minus 2 squared plus 5 times x cubed minus 2 minus 1. And this would be f composed of g of x. All right. We can do the opposite. All right. If I took f and I want to put f inside of g, all right, f inside of g. Well, I would then take this and look at it, and if I erase this part right here, okay, f composed g. So what does that mean? That means I'm going to be taking this function, whole thing, this is f, and plugging into g. And here's one slot for g, so I'm taking all that and substituting in for all the placeholders, x values, inputs for g. So I would have simply x squared plus 5x minus 1 cubed minus 2. And that would be g composed of f of x. And that's what we have. You see a lot of different composite functions wherever you go, because you see a lot. You see almost a lot in trig. All right, here's just another example. And what you want to do is be able to decompose, all right, these functions. For example, if you had this function h of x, which was sine squared of 3x. Now this is a little bit harder. Now we've got sine squared of 3x. This would actually be the same thing as sine of 3x, that quantity squared. Just so you know, that's what that is equivalent to. Now, if you remember decomposing, I actually have, well, how many different layers? Well, you have a layer outside, so I'll call that f of x. The outside layer refers to this section right here. So I figure to be x squared. The next layer, if I change the color to black right here, the next thing inside is the sine function. All right, the sine function. So now I have this sine function, so I'll call that g of x. G of x is my one inside, so it'll be sine of x. And the function right after that is the one inside of the sine, which is this right here. All right, and we'll call that, I don't know, I'll call it j of x. Yeah, there's going j of x. All right, j of x, which would be 3x. So if I were to write this composite, what is h of x going to be? Decomposing this, this would actually be, well, f with g inside of that, with j inside of that function. Or f composed of g composed of j of x. So you can have several composites of different functions inside each other. So that's how composites work. All right, composites are like ogres. All right, they're like ogres. They have which are like onions or parfaits, whatever you prefer, but they have layers. Okay, and hopefully that helps you out. And we're going to have another tutorial on how to do this with some graphs and other functions.